In this video, we'll be looking at descriptive statistics and inferential statistics. As scientists, we have many questions that we wish to answer, such as how many people do we need for a particular experiment? Are the results we find meaningful? Are they accurate? Do they represent the wider population? And are they replicable? So can we find the exact same effect multiple times with multiple populations? We might also care about how many people do we actually need in a study to be able to make such statements. Are 10 people good enough? Probably not. But what about 100, 1,000? The population of the planet is pretty big. How do we know how many people we actually need? And if the results that we find based on smaller samples are representative of the bigger population. And this is why we use inferential statistics, because we want to reliably and accurately estimate population effects using smaller samples. It's also because we want to reasonably assume that the effects and relationships that we uncover are not due to chance or error. And after we do find the significant results, to understand the level of uncertainty around these estimates. Descriptive statistics allow us to summarize our data and maybe provide some insight into what the data actually contains. So we can do this either numerically through tables that contain central tendencies, variations and dispersion, or even the shape of the distribution of our data. But we can also do this, of course, visually using different methods such as bar charts or pie charts in order to display the shape, the relationships, even the differences that we might have between different groups. So there's a lot of flexibility, but the issue is that even if we do identify potential patterns or differences, in the absence of inferential statistics, we cannot make claim that these differences are statistically significant. So if you recall from the previous video, the type of descriptive statistics and even inferential tests that we can do differ based on the type of data that we have, with ratio data allowing us more flexibility what we can do and how we can represent this data, while things like nominal data having much more limited in terms of the statistics that we can run. As a brief overview, for nominal data, the type of descriptive statistics that we have are things in terms of contingency tables, where we are basically only counting the different categories of data that we have and how many occurrences for each category that we have, as well as totals for each of the dimensions that we are looking at. In terms of location statistics, all we can do is report the mode. So this is the most popular out of the options that we've provided individuals for responding. While in terms of variation and distribution, we can't say anything about this because nominal data is unordered data that does not follow any distribution. With ordinal data, we have a bit more flexibility. So just like with nominal, we can also report things in terms of frequencies and counts. But in this case, we can actually say a bit more about how our data is distributed. So for example, we would normally mention the median. So this would be the middle value, but we can also use the mode if that is more appropriate for the type of scale that we use, as well as something like a 5-number summary. So what this does is allow us to communicate the maximum, the medium, and the quartiles for our data. So it provides a bit of an overview of the type of distribution that we have. For interval and ratio data, we are basically allowed to do any sort of operation that we find to be relevant and informative. So in terms of descriptive statistics, we can measure the number of observations, we can use counts, frequencies, sums, averages, any of the things that you think would be relevant to your reader to communicate the information about your data. In terms of location statistics, we can report mean, median, maybe even mode if that is relevant for your data set. In terms of variation, we can report standard deviation, standard errors. We can also use a 5-number summary, and this is normally represented as a box plot. But we also can report confidence intervals around the estimates that we actually have, and even make statements about the shape of our distribution in terms of how skewed it may be, or how flat or how tall. As I mentioned at the start, inferential statistics are used to examine relationships between variables within a specific sample, and then make generalizations or even predictions related to the larger population. Such tests allow us to make statements about relationships, differences between groups, or even change over time. However, importantly, these types of tests rely on specific data assumptions that we have to meet in order to conduct them, such as normality of distribution, the homogeneity of variance between different groups of data, and there being no outliers within the data we are actually testing. In this video, I'll be covering the assumptions for Pearson's product moment correlation and students or Welch's two independent samples t-test. There are, of course, other tests that can be conducted even on this type of data, but these are the most common and the ones that will be most relevant to you. Pearson's correlation has several assumptions underlying the test, meaning that if you do not meet these assumptions, you cannot use the correlation. So some of it are normality assumptions. So this means that the data you are looking at is normally distributed. Homoscedasticity, which means that the variance of the two variables you will be comparing with each other are the same. Linearity, which refers to the shape and the relationship between the two variables. So we're hoping for it to be a linear fashion and not have any sort of curvatures. That the two variables you're looking at have a continuous distribution. So this means that they must be continuous variables, either of the ratio or interval scale. Importantly, the observations must also be paired, meaning that how many you have in one variable you must have in the other one, otherwise the test will not be valid, and that there will be no outliers within your data set. It is important to note that if you fail any of these assumptions, you cannot use Pearson's correlation. When testing normality assumption for correlations, this is rather straightforward. All you need to do is create a histogram for each of the two variables and visually inspect them to see if they kind of follow the normal distribution pattern. So the way you do this is you go to Analyze, Descriptive Statistics, and then Explore. You would add the variables that you care about within the Explorer's dependent list, and then you would click Plots. You would click histogram and normality plots would test. This will provide you not only a histogram of each variable so you can inspect it and see if it follows the normal distribution, but will also give you the test of normality, which the one you care about is the Shapiro-Wilks test. If this test is significant, that means that you can assume your data is not normally distributed and you would not be able to use Pearson's correlation. If it is non-significant, then you are free to assume that it is normally distributed and you can use the correlation. For homoscedasticity, the way to test the assumption is a bit more difficult, but following these steps, you should have no issues. You would go to Analyze, Regression, and Linear Regression because, yes, the way to analyze if your data is homoscedastic is to actually run a regression on the two variables that you're interested in. In here, you'll be able to select one of the variables to put in the dependent column and the other variable to put in the independent column. Next, you would click on plots. You would put in the standardized residual, so this is the Z resid. You'd put it in the Y variable, and you would put the dependent within the X variable, and then you'd click continue. What will come out would be a lot of output. Most of it you can ignore, but the thing you care about is the scatter plot. So ideally what you're looking for is after you add a line of best fit, you should look at the data points and they should be roughly equidistant to each other. So you should not have huge discrepancies where some points are all the way on the other side while some of them are bunched together. They should kind of look like this, where they are spread out pretty evenly along this line. The linearity assumption is pretty easy to verify. All you need to do is create a scatter plot of your data. So basically you would go into chart builder, select scatter and dot, and you would select a simple one where you would put one of the variables on the y-axis and the other variable on the x-axis. When you run this analysis, you should get out a printout, which should technically follow a linear relationship. This is important because if your data does not follow a linear trend, so if it has, let's say, an upward bend or an S-shaped, you cannot assume that it is linearly related, and a Pearson's product moment correlation would not be the correct method to analyze such data. With respect to the assumption of continuous variables, this is something that you, of course, would need to determine beforehand. You need to know what type of data you're actually looking at, and if the two variables are not either interval or ratio, then this type of analysis is not appropriate. So this is something you need to decide beforehand to make sure that you're running the correct analysis. Similarly, in terms of paired observations, this is something that you need to inspect within your data set to make sure that the two variables you are comparing have equal numbers of observations. So in this case, if it was something like this, then the actual correlation would stop here. These values would be cut because there is no way to run a correlation if it doesn't have a paired observation in the other variable. So this is something you need to make sure of. If you remember from the previous video when I mentioned missing data, this is another place where it is important. It effectively shrinks your sample size and it would stop here. To check if your data contains outliers, which are very impactful in the correlation analysis, you would use the procedure that I mentioned last time, where you would calculate standardized scores, so z-scores, for the two variables that you care about. So the way you would do this easily in SPSS is you just look in descriptives, you would add the two variables you care about, and then you would simply click the button that says Save Standardized Values as variables. You click OK, and then you will have two new columns with the z-scores for the two variables that you care about. And then you would use the procedure I mentioned last time where you would check if any of the values are higher than 3 or higher than -3 on the z-scores. If they are, you can consider them as outliers. Okay, so let's say you run through all the trouble of checking all of those assumptions. What do you do if you fail any of them? So realistically, if you fail things like the normality assumption or homoscedasticity, I would just recommend you change over to the Pearson's rank correlation analysis. This is another option that you have in SPSS, which is way more robust and would not have an issue with any of these points. So it's something to understand, because if you do fail these assumptions and you report the Pearson's correlation, your answers may be wrong. So the assumptions that you're making matter, and the data that you are analyzing also matter. The results that you will be reporting must be correct. So if you haven't checked these, make sure to do in advance. If you pass all of them, you're free to use Pearson's correlation. But if you have any issues, you would need to use an alternative solution. And the one I recommend in most scenarios is Spearman's rank correlation. Moving over to the t-test, this too has a lot of assumptions that you need to make sure follow your data. If not, you need to again find alternative solutions. As with the correlations, this one assumes that you have continuous variables, that normality holds for your data, that your data is homoscedastic, and you do not have any outliers. Unlike the correlation analysis, this one assumes that the data points come from two separate groups and the observations themselves are independent, meaning that you are only looking at two groups, not more than two, and if participant 1 has a particular data point in group A, they cannot also have a data point in group B. So if your data does meet all of these assumptions, you're free to use the t-test, which in essence what it does is compares the distribution of one of your groups with the distribution of the other group. And if the difference between the two of them reaches statistical significance, then you can say that there is indeed a difference in performance or any other metric between the two conditions. How large the difference is not determined by statistical significance, but by effect sizes such as Cohen's d, which would be able to give you some insight into how large the difference between the two conditions may be. With respect to the first assumption, this is quite straightforward. All the t-test really cares about is that you're only looking at two independent groups at a time. So for example, if you'd look at gender, it will be fine because it only is split into female and male, but it would not be okay if you have a variable that contains more than two levels. The only way you could do this is either analyze it through an ANOVA, which does allow for multiple levels, or you would have to conduct individual tests between each of the two categories, and then you would have to apply some corrections to the output because you are running multiple tests on the same data set. As for independent observations, this should be quite straightforward. It just means that if an individual belongs to one of the groups, they cannot also belong to the other group. So this is important because if you do have repeated values, you would not be able to use the independent t-test. You need to use the paired samples t-test. So in this case, you are only looking at two separate and independent groups when you are comparing data. As we saw with Pearson's correlation, the t-test relies on the assumption that your data is continuous. So you'd ever have two scalar datas. So this may be ratio or interval. These are the only ones that you would be able to analyze. So whatever group variable you have, the measurements would need to be in a ratio or interval format. Otherwise, you cannot use student's t. To test normality for a t-test, it's quite straightforward and you have multiple options at your disposal. One thing that is important to note is that you may need to split your data file, as I showed in the last video, beforehand, so you can actually create histograms for each of your variables separately. So for example, if you were looking at student performance, you would first need to divide the data set based on, say, gender or course. So then when you run your histograms, it produces two independent plots, and you can check if the distribution of each follows a normal pattern. However, you're also free to create QQ plots or even box plots to be able to see the symmetry of your data if it contains any outliers. So you do have some flexibility in the options that you can use. If you want to have more concrete numbers, you can always go into the Descriptives tab, and in the options section you can click kurtosis and skewness, and this is going to show you the way your data looks like, and you have some cutoff criteria to know if your data is either skewed or displays kurtosis. If the values are higher than these cutoff criteria, you can start to suspect that there are issues with your data and you might not be able to use the t-test. If you want an inferential statistic to go along with this, I recommend the Shapiro-Wilks test. This is normally very robust and useful for all sorts of data, and the way you would do it is when you select the option to show test of normality, it's always going to produce this output, and what you're looking for is the Shapiro-Wilks test. If this is statistically significant, then you can assume your data is not normally distributed and you might need to do something to correct it. But if this is statistically non-significant, like it is in this scenario, then you are fine to assume your data is normally distributed. As for the homogeneity of variance assumption, this is quite easy to do because it is a default feature of running any sort of t-test. So when you decide you want to run the t-test after you've checked the previous assumptions, it will output this table that contains the t-test itself, but also Levene's test for equality of variance. If this test is statistically significant, then you cannot assume you have equal variance. So this assumption would be violated. In that case, what you would need to report are the numbers related to the equal variance not assumed, which is actually Welch's t-test. So this is what you would report if Levene's t-test was statistically significant. For outliers, you will do the exact same procedure that you would do for the correlation test and the one that I outlined in my previous video. So you would need to, again, first split the data based on the groups you will be looking at. This is always good practice because what may be an outlier in the overall sample might not be an outlier when you consider the grouping variable. So first you split your file, and then you simply create z-scores for the variable that you will be analyzing with the t-test. And again, you use the criteria for if it's higher than +3 or higher than -3. In that case, you would consider that that might be a potential outlier. So what I would recommend to do is first run the analysis with the outlier, report that, then take out the outlier and do the analysis again and report that as well, mentioning any differences that may have occurred. So finally, once more, after you've done all of these different assumption checks, what do you do if any of them actually fail? So what if you violate any of these assumptions? In terms of normality, if you have a huge database, it's not something that will be a major issue. It might have a small impact on your results, but not something that you should worry about. But realistically, if there are any problems with normality, I would recommend, again, you just report Welch's t-test. So this is the one that says equal variance not assumed. In general, this has become recently the best practice in terms of reporting independent samples t-test is regardless of the situation, simply report equal variance not assumed instead of the student's t-test. The only time it's more optimal to report student's t-test is if all the assumptions seem perfectly fine. In terms of homoscedasticity, again, if your assumption is violated, use Welch's t-test because you have not learned how to transform data, and Welch's t-test is pretty robust to homoscedastic issues. With respect to outliers, as I mentioned, you basically have the only option of first you run the test with the outlier included, then you take out the outlier, justifying why you did so based on the criteria, and you would run the test again and report the new values, mentioning any differences that you would find. Of course, if you would be a bit more advanced, there are other robust alternatives to deal with these types of situations, such as Ewan's t-test, but this is not something that you need to learn about at the moment. So that's it for today's video. I will not be showing these into SPSS at the moment. I will be covering these steps in the next video when I'll be detailing how you actually conduct all of these tests, how you interpret them, and then finally how you report them. But you are free to try these methods out yourselves. Follow the steps that I mentioned within the video using any database that you might have to see how it kind of pans out. And then the next time you'll be able to see how I would actually conduct these analyses and how I would report them in full so they are transparent and accurate. Good luck.